Hello and welcome to another coding ASMR video, and today we're gonna work with some data. And I have this Kaggle challenge open here, which is the Tabular Playground series from Kaggle, which is like a beginner dataset. It says here, practice your ML skills on this approachable dataset, so it's not super challenging. I already downloaded the data and I will be building a PyTorch model with that. We can see here on the leaderboard that a good score is 75%, so that seems kind of low, but that's like the best score that people got. Alright, so we are already connected to our virtual machine over here. I uploaded the data onto my Google Drive, and the good thing about Google Colab is that you can connect it to your Google Drive. So let's just do this right now. So from Google Colab, import drive. Alright, and then we will use this and mount our Google Drive on the path content drive. Okay, and now we will copy from that. So from content drive, my drive, that's just how Google calls it, and then we will import the test CSV zip and put it into just the content folder. So content test CSV zip. Now I need to click this link and insert an authorization code. And now, yeah, we see it here. And let's do the same with the train dataset. And there's also a sample submission. So let's copy both of these as well. And then we want to unzip all of them. So unzip -q, and then we will unzip the test CSV zip into content as well. And same with both of the other zip files. And now we have the test CSV, the train CSV, and the sample submission CSV all unzipped. So now let's work with the data. Let's call this data exploration. Okay, so for that part we want pandas, and we import that as PD. And now we can read the CSV files. So train data frame will be from pandas.read CSV, and we pathed the path, so content, and then train CSV, and the index column will be ID, and you can see this on the Kaggle data. Alright, execute this, and this takes a while because this is quite a large file. Alright, and now we can look at how many rows and columns we have. So print number of columns, and that's including the prediction. So we have some features and a target, which tells us because we're doing a binary classification, the target will be either 0 or 1, but we'll see this in a bit. So all the columns are the length of train data.columns how many data points do we have? That's the number of rows. And that will just be the length of the trained data frame, not trained data. Let's change this. Okay. If we run this, we see that we have 101 columns, which is 100 for the features and then 1 for the target, obviously. And we have 60,000 rows, so 60,000 data points. Okay, now we can take a look at the columns. So trainDF columns will tell us the names of the columns from the CSV file. So we see that they are very creatively named, so they're like F0, F1, F2, up to F99, so that's in total 100. And then we have the target column, and if we take a look at one of those, I believe we can do it like this. So F0, then you see that we have the ID as always, and then the values, which are like around 0, and they're like floating values, and this one is a bit higher, that's 1.3. And if we now look at target, then you see that they are 0 or 1, because that's what we want to predict, and it's a binary classification, so there's only 2 options. Alright, we can take a look at a bit more of the data in pandas by doing train data frame.head and executing that. And then we see a bit more, so we see the first 5 rows, and yeah, and then at the end we see the target. And then we can also do train lit frame dot describe, and that gives you a better overview, so you can see count. So if one of them would be missing, they all wouldn't be 60k. And then you can see the mean, so you can see that the F0 column is comparably small with a mean of 0.3, and the F2 column has a mean of 300, so that's quite large. And you can also see the standard deviation and the minimum, as well as the maximum and some points in between. So the first 25% from the minimum to the maximum end at the value 0.02. So this gives you like a bit of insight, and you see that this is quite large, and most of them are like around 2 or even smaller, and this is like an outlier, so to speak. Alright, but now let's see if there's any missing values. And we can do that by using train data frame is null, and then this gives us false for every entry that is not null. Now this is not particularly useful, you can't even see all the rows because it's so big, but we can do any, and then this is only true if one of them is true. So now this tells us if there's anything in a column that is false, that is null, and then this would be true, but they are all false, so they are all not null. And if we do any again over that, then this aggregates all the columns, so we know that there is no missing value at all. So that's good, we don't need to insert any of the missing values with new data. So now let's split the data. And for that one, first we need to split the features, commonly called X, from the target, so that's Y. So the features are the whole train data frame, but we drop one column, and that's the target column. And to tell it that we want to drop a column and not a row, we tell it X as 1. And then data targets are just the train data frame and then target. So let's execute that and then just look at data. So now you see that's just this one column, and data features is this whole table again, but it doesn't have the target at the end. It just goes to F99. Now, because we only have a train and a test dataset given, we also want a validation dataset. So for that one, let's import from sklearn dot model selection the train test split function. And now we can get xtrain and xval for validation, and ytrain and yval with the train test split data features and data targets. And we can tell it that we want the test size, which is the validation here, to be 0.2 of the whole dataset. And to make it reproducible, we can do random state equals to 3, for example. The next thing we need to do is pre-process the data, and that mainly means we need to scale it, because earlier we saw that some features are like 300, and you can't have that, especially not with neural network. They will not converge at all. They don't like that. They need ideally zero-centered data, and with a variance of only at most 1. What we do is we use the sklearn standard scaler, which will standardize the data. So from sklearn preprocessing, import the standard scaler. I always want to write it with an A, but that's wrong. And we initialize this. And then we fit it on the training data. That's important, because we don't know the test data or something during at the start. We get like test points in a production environment. We get them like bit by bit, so we can't use all of them to calculate a mean or anything. So we will just fit the scalar on the training data. So that means scalar.fit, and we pass the xtrain in it, and then xtrain scaled will be when we take the scalar and we transform the data. Oh no, first we need to transform training data, and then we do of course the same with the validation data. And I think the output of this is now a NumPy array, because that's what sklearn does, which is fine, because we wanted, in the end, we wanted to be a tensor for the neural network anyways. And now we get to the good part, or the not so good part, depends on what you like. And we use PyTorch to create and train a neural network. First of all, let's import some stuff. We always need just simple torch, that's PyTorch. Then we often need the torch.onin package as an n, and then we already know that we need a dataset and a data loader. We need to convert our values that we just normalized into a dataset. So from torch utils data. let's also import NumPy. Okay, so now we create the dataset, and let's call it binary dataset, and that extends the Torch dataset class. First save the x and y values, and then we also need to implement the length method that's given by the PyTorch library. Then we need to do that, and that will be the number of data points in the dataset, and for us that's simply the length of the input array. You could also do the length of the target array, it doesn't matter, just return one of them. And then we also need to give it a getItem method, which receives an index and needs to return the same point for the index every time, obviously. And we need to return two things, so return x and y. And let's do them separately. Let's scroll down a bit. Okay, so x will be self input array of the index, but then the whole thing needs to be a tensor, so we will put it into Torch tensor. And then another thing that's important is the type. So the values in it, so the D type of the array or the tensor needs to be float, and we do the same for the target. So target array of index, and also set the D type to Torch float. Let's also immediately create our model class. So let's create the linear network, which will extend the NN module class from PyTorch. And this of course also has an init method. And then that we need to call the super init method of the NN module, and we pass it the current class, linear network, and the self instance, and call the init function of that one. We will use linear layers, as you might have imagined, and the redo activation function, and we'll just create the sequential stack of it. So this will be a sequential, which is it just puts all of the layers together, and we start with a linear layer, which will be in the NN package. And our first layer has 100 inputs because, I mean, we have 100 features, so that makes sense. And now we can arbitrarily upsize, and let's just try 512. And then we need to follow this up with a redo or some other activation function. And then we can do the next layer. And this number now has to match the output of the previous layer, so 512. And then we upsize even more to 1028. Again, add a redo, and now we can go back down again a bit. So from 1028, go back to 512. Don't forget the redo. And then the output needs to be just one neuron, because we just want it to tell us if it's 0 or 1, or the probability that it's 1. And then this of course will also tell us the probability if it's 0, because it will just be the inverse of it. To make it generalize a bit better, we'll also insert some dropout layers. So you can just put this between here, just say dropout, and you give it a probability. And what this does is, during training, it will, with a probability of p, it will take some of the neurons and zero them out. This will prevent overfitting, because the network will always have some blind spots and they change every iteration. And so the network needs to adapt and like be a bit broader, so the few blind spots don't completely make it blind. So that's like the rough idea here, but that's a common thing to do to avoid overfitting. We'll also do it here, and after the big layer here too. Alright, I think I forgot the comma up here. And then that's it for our layers for now. And we also need to implement a forward method where we get an x, so an input. And in this network it's super simple. We just put the x into our linear relief stack and just return that. Run this. Now let's create our datasets and data loaders. So let's do the train dataset. This will be a binary dataset, and we just said we need to pass in the input and target array. So that's xtrain scaled, and because the target, the Y train wasn't scaled, so let's, oh, I put in a text, that's not good. I wanted a code. So because the Y train is still a data frame, we wanted to convert it to a NumPy array first. So it's the same as the xtrain scaled. So we do NumPy array of Y train and create that dataset. And we do the same for the validation dataset. And with the datasets we can create our data loaders. So train data loader will be data loader, and we pass in the train dataset, the batch size. Let's create some hyperparameters for that one. So batch size will be 128. They're like fairly small data because they're like only 100 numbers, so it's not like images or something, so this fits into the GPU easily. So this will be the batch size, and then also shuffle equals true, so it will always like reorder them, so it won't be the same batches in every epoch. Instead they will be a bit different, which is better. The validation data loader will be quite similar. We use the same batch size, though we could use the maximum batch size which fits into memory, because we're not concerned about the training effects of it here, but I'll just use the same. I haven't tried which one is the best for this memory. But to compare performance, it's important that you do shuffle false, so they test the same thing again and again, and it's not changed in any way. Alright, so if we now run this, we get an error, and it actually took me a while to find it, but you might have seen it while watching, and you might have been slowly going insane that I just forgot to write this. But yeah, here in the dataset I set the input array to the input array, but I never set the target array. I don't know, stopped writing apparently. So we of course also need to set the target array, and then hopefully that should fix it. Yeah, so we get the little green check mark that everything ran. Now what we also need to do is create a device, which will be CUDA if torch CUDA is available. So that's basically just checking if we have a valid GPU on which we can calculate, and we'll output this just so we know. Okay, let's just do this. Yeah, and because I haven't set up any GPU, I think I can do it here. Do GPU, but we're not even training right now, so I think I'll just skip that. Right, now it's time to create a model, which will be a linear network, of course. And now we want to put it onto the device. We can also print the model. And now we see the architecture and that the bias is true and all of that. We also, of course, need some way to evaluate the model, and that is the loss function. And because this is binary, we will use the binary cos entropy loss with logits, because we haven't done a sigmoid layer in our dataset, in our model I mean. And we also need an optimizer. These are in Torch Optim, and now we could use, oh, that was actually a great overview. Yeah, there's like Atom, Atagrad, there's also SGD. Let's just use Atom, and you need to pass in the parameters of the model that you want to train, and then an initial learning rate. I'm using the default here, and some weight decay to try and regularize the model so it doesn't overfit as much. You don't necessarily need that, but I'll add a learning rate scheduler. Just use the simple step LR, which you pass a step size, and you can say, look, every X epochs, let's just say every epoch, reduce the learning rate or multiply the learning rate with the gamma factor, and in that case it will always be reduced by 10%. Alright, now we need to write the actual training code. We need to create a train function. I mean, we don't need to, but it makes sense to write a function where we train one epoch, and then we can call this function again and again. So this needs the data loader and the model, loss function, and the optimizer. It doesn't need the learning rate scheduler because we do the learning rate schedule step after an epoch has finished, so it doesn't need to be in the epoch. Okay, so what's very important is that we say model train, and this toggles things like the dropout on and off, and we want to keep track of our correct predictions so we can look at our accuracy and also the train losses. And then we iterate through the data loader. And we enumerate it so we can see where we're at. So first we will put both of the values onto the device. And to compare with the dimension that comes out of the network, we need to unsqueeze y, otherwise it would be the size of the batch, so for example 128 as we currently have it, but no second dimension, and the thing that comes out is 128 by 1, so there's a mismatch when you want to compare them. We put the features through the model and compute the loss on the predictions compared with the true target y. Then we zero out the previous gradients before creating new gradients by calling backward on the loss. Then we adjust the weights. And we also save our training loss for consideration later on. And we want to see how many values are correct. So for that, we first need to put the prediction through a sigmoid function, and then this will give us a probability. So before it's just some weird zero-centered value, and to make it a probability between 0 and 1, you need to put it through the sigmoid. And then if it's bigger than 50%, that means we'll treat it as a 1. So this will give us an array of true and false, but we don't want true or false, we want it to be either 1 or 0. So we multiply it by 1, and now we can compare it to y. And then we can sum them all up, because then all the trues, all the ones that were the same, will be counted and added. And then if the batch is like a multiple of 200, maybe we'll change this later. Not the batch, the batch. Why did I write batch size? Batch index. The batch index that we're currently on is like a multiple of 200, then we want to print current loss item. Right. And at the end, for our accuracy, we will take the correct values and divide them by all the values, so the length of the data loader data set, because the data loader, the length of that will be the amount of batches we have, not the amount of data that we have. And we can also return all the train losses, so we can use them later to look at the whole training loss curve. Let's try this. So we need to call train epoch with the train data loader, a module, a loss function, and the optimizer. Now it tells us the current loss, 0.695, and now it went slightly down, the 5 went to a 4. I'll just let this run for a bit. Okay, so I changed the runtime to GPU because this was taking way too long. I let it run and it took like 2 minutes just for one epoch. So now we're on GPU and we can see the training loss. It's not going down as I would hope. Like you can see it goes down to like 0.55, 5.3, but then back up to 5.5 and 6.1, and then even back to 6.6. So if you have any more ideas on what exactly is happening or how I could improve my hyperparameters or anything, let me know. Not an expert. But yeah, that's one epoch, works fine. And now let's also write some code to test the model. It will look very similar, but with a few less steps. So to test one epoch, or to test after every epoch, we again need the data loader and the model and the loss function, but not the optimizer because we're not changing the model in any way. So this time we will put the model in eval mode. Want to have a test loss and also a counter for the correct values again. And this time we'll just take the average train loss. We don't need to save every single one of them. Okay. So we don't want to compute any gradients, so torch no grad. And then again for x and y in the data loader, which will now be the test or validation data loader. Again put x to device and y. Now we just add all of the losses up, and then we can divide them at the end and get the average. And the correct counter will be the same as above. So in the end, we have the test average loss. This will be the test loss divided by the number of batches. So the length of the data loader. Well, one word, data loader. And then the test accuracy will be again the correct types of predictions divided by the length of the data loader dataset, closing brackets. And we can again return the test loss to plot it. Of course, we need to have a closing bracket here, segment of predictions, and then this bracket closes with this one, this with this one, and this with the first one. Okay, let's try again. Okay, now it runs. Now let's test an epoch on the val data loader, model, and loss function. Oh, both of these should be initialized with a 0. Now it seems to run, and oh right, we also want to return the average test loss, so length length of data loader and just gives us the returning value. Now let's set up a few epochs. Okay, so let's say epochs 30, and then let's save the train losses and the test losses so we can look at them. And then for T in range epochs, print epoch number T. I mean, this will then start at 0, that's not great. T plus 1, and let's put a few dashes. And then we will want to train an epoch with the train data loader. And this will return all the train losses, so we want to add them to the overall list. And then test one epoch with the val data loader, the model. Add this one to the test losses, that's a single value, so we just append it. And then let's not forget the learning rate scheduler step. Now let's reinitialize the model, everything back from scratch, and do 30 epochs. Let's go. Alright, and through the magic of editing, we're done with training. We trained until epoch number 30, and we have a training accuracy of 47.2 and a test accuracy of 47.5. And on this data set, the leader on the Kaggle data board had 75.2 or something. So like, it's okay. If you have any more tips on like small things I could change, please let me know. Always interested to hear from others. But since we did save the loss, let's look at that. And for that, we will get matplotlib, and then I got this nice function from Stack Overflow, like you do, because as you will see in a bit, taking just the normal loss, it's incredibly noisy. So I took some moving average. You can do it with the convolve function, which if you let it convolve with a ones array, then it basically does the same as the moving average if you then divide it by the width of which you want to compute the moving average. Right, let's take this, and now we can see, let's just plot the train. That's not how you do it. NP the range of the length of the train losses. We also need a second closing parameter. And yeah, basically you can see nothing at all. So that's why I took the moving average. Of the train losses over like 400 iterations, because you can see we have like over 100,000. And then we plot that one. And now you can see that we have indeed a steep decline at the start, but then it just like continues in this weird noisy slope, and it doesn't really go any deeper. Like it continues a bit downward, but at the end it kind of stagnates. So yeah, that's that. I don't have much interpretation of that because I'm still learning myself. But let's do the same with the test losses. And yeah, here we can see that we also get down quite quickly, but then we just sort of like the minimums stay at one level or kind of even go up at the end here, so like there's no sort of improvement here anymore. So that's it for today's video. Thank you so much for watching, and hope to see you in the next one. Bye!